Good evening, and welcome from the woods of Maine. This is part 3 on 1.2 billion years of Earth history in the New England area, with some focus on the Marginal Way in Agunquit, in my hometown, as well as Mount Washington and Mount Katahdin. Of course, we haven't got there yet. This is a fairly long lecture, about 280 slides, and I think I'm at slide 50, so there's a little bit more time to go. But in any case, I ran through in the previous lectures plate tectonics, formation of the Earth, a little bit of review of some of the things we'll be going over, large igneous provinces, lips, and stuff like that. Basically, the fundamental tools for what we would be using to understand this particular lecture. So I basically left off where I built North America. I went through at least 6 or 7 orogenies, but just in very quick fashion. Each one of those orogenies could be a hour, 2 hour, 5, 7, 20-hour lecture in itself. But that's for a different lecture. So in any case, let's get to it. And so now we're going to look at the supercontinents. I built North America. North America in this particular case is referred to as Laurentia, and it will be that way up until about 200 million years ago. And once Pangea forms and then breaks up, then we have North America as we remember it, or as we know it, rather. So supercontinents through time. We think that there was a group of them around 2.5 billion years ago. And whether or not they came together, and we're going to use the word supercontinent very loosely here. We may have had some pieces of cratonic mass that came together and formed little cratons, and maybe they banged into each other. But we know that something happened about 2.5 billion years ago, because for one thing, it switches from the Archean time to the Proterozoic, and it's marked by a few things, especially one being the great unconformity, as well as a change in rock type, and definitely something happened. So what is a good theory is that the pieces of felsic crust that had formed at that time, and they were small, began to start to coalesce and bump into each other. Just as if you put leaves on a pond, they'll eventually bump into each other, and they'll eventually separate, and then they'll bump into each other again. It's just the way it is. So some names that we have used for this super, we have, you may have heard the term Valhalla. It's used to describe an ancient supercontinent. There's a few other names, but this is interesting. This is the superior continent that one of the first things I did when I built North America. And you have the Slave, the Wyoming, the Ray, and whatever. You can't really see it in here, but this is North America right here, and this is the nucleus of it, and what's going to build to be the actual continent. About 1.5 billion years ago, we have one called Nuna or Columbia. Both names have been used before. By the way, I believe that the name for this one is U-R. I'd have to go back and look, but I do remember that. But I know that Nuna is also really, it's also can be termed with Columbia. This is a supercontinent about 1.5 billion years ago. You have Laurentia here, Baltica. This would be I believe this is North Africa. This is Siberia. This is the Indian subcontinent. West Australia here, maybe. Maybe Antarctica here. We know that these eventually got pounded onto the west side of North America. By the way, the east coast is right here. So we've actually rotated, since this time we've gone here, so almost 180 degrees in 1.5 billion years. The next continent, this broke up. It finished breaking up about 1.3 billion years ago and then started to come back together. around 1, and this is the supercontinent of Rodinia. This is one of our, aside from Pangea, this is one of our most studied right now. It is one of the ones that we know most about, Laurentia really plays, or North American Laurentia plays a very important part in this, and it almost is as if it's the key, because everything else kind of comes together around it, or so we think. You have Amazonia here, and this would be Maine right here. We are now starting to rotate counterclockwise about 25, 30 degrees. Baltica here, Greenland, Siberia. Siberia is making its way around to the other side. And then we have South Africa, North Africa here, I believe. I don't know what the names of some of these. It's India over here. This is, oh God, that's a, can't think of the name right now, but this is part of Africa. In any case, so this is Rodinia, and this existed from about 1.0 to about 0.7 billion years ago, or 700 million years ago. And then when this broke up around 700 million years ago. Amazonia right here bailed this way. Baltica went that way. North America or Laurentia began to continue its counterclockwise spin. Siberia kind of stayed here. And then we had an ocean form right here called the Iapetus Ocean, which is going to come into, this is a big part of our conversation coming up. And then these came back together about 250 million years ago and made Pangea, which is our last and pretty much our most well-known supercontinent. You have what we would call Eurasia here, which is North America and Asia, Siberia, and then you have what we call Gondwana down here, which is the southern hemisphere subcontinent. Supercontinent that consists of Africa, South America, Antarctica, Australia, India, and then this breaks up about 170 million years ago, and just come right here to make this present time in between here. This will eventually converge back together again, and we're going to make what we have, I've heard it called Neo-Pangea or whatever, but this is going to be the supercontinent 200 million years. Now, very hypothetical. We are looking down, I believe, from the North Pole at this one. So the North Pole would be here. Greenland is literally on the North Pole. The Arctic Ocean closes. The Atlantic does close between South America and North America. However, Africa moves away and bulldozes into Europe and Siberia. You've got India over here, South China. That might be Australia there. So this is very hypothetical. We don't know really. I mean, it's an idea. We're just basing it off the way the continents are moving at present time. This is Rodinia about 900 million years ago. Kind of a more detail of it. So what we have here, we are located here. This would be Maine. Off immediately, you have to understand that this is just the configuration as we'd see the continent today of North America. It is not like this. Believe it or not, the equator is something like this. And we are south of the equator at this point, or at least we're going to be moving south of the equator. In any case, the Grenville, no, we are south of the equator. The Grenville orogeny goes from here, right up through here, around here, and through here. That African one was called Kalahari, by the way. And this is a huge mountain range. It probably rivaled the Himalayas in size. And as I said, there's pieces of New England that are, or the East Coast rather, that are welded onto Argentinian side of the Amazonia is just basically the root of South America. And so a piece of this stuck off, and we have pieces of it over here, and then a piece of this right down here went away with that. So we know that the sediments that made up some of the Grenville clastic wedges, basically sediments that form adjacent to the mountain ranges once they begin to erode, that they match zircon grains of Amazonia and not Africa. And this is important because this tells us that this was here and not here. So this was a different, and when this breaks up in another 200 million years, this is 900, there's going to be a new ocean forming here, and that is the Iapetus Ocean. Waiting for it to respond. There we go. All right, so this is Rodinia, 750 million years, a little simpler. This is, there's different variations of what we think Rodinia really looked like. You know, we just know that for the most part, Laurentia was the center. This one depicts Amazonia and Baltica a little bit further north. This is part of my, believe will be part of the Argentina area of the Amazonia subcontinent. I'm sorry, Craton. We got Australia, East Antarctica over here, the Congo, South China and Siberia. I don't know where India is. It's not on here, but it's in there somewhere. And these are samples that we've taken, and this is how we determined each one of these. We basically did a geochemical analysis on it, and we figured out that, you know, this Craton has a signature of certain, chemical properties, as well as this one. They're all different slightly. And so when you take zircons from these very small little grains that they have nuclei in them, atomic nuclei that we can use to date, and they also carry geochemical signatures, and we can tell which continent they derive from, especially the sediments, and more so the initial volcanics that come out when continents collide, mountains erupt, mountains are built, volcanoes erupt, and over time they erode, and then we find the signatures of these, basically around what was once the mountain. So there's just another. So it is also possible, 200 million years, that Amazonia could have rotated this way across a fault. So nothing's set in, pardon the pun, but nothing's set in stone on this. Rodinia tectonic map, which is much more complicated than anybody would want to take a look at besides me, so I'm not going to go into it in huge detail, but it tells a lot. This is the Maine mountain belt right here. This is a very funky map. This is the equator right here, so it's really a very strange orientation, but it's telling me that we are below the equator, south of it. This is the South Pole. We are actually facing southwest. And we are the East Coast, so we need to spin almost another 90 degrees or more for this to orient itself, and it will do that eventually in the next 700 million years. Baltica, these color codes are just telling you, the mountain ranges and what was involved in building, but we're not going to go into that much. So maybe I'll do I think I want to do a formation of Rodinia. I just haven't got to that point yet because it's a bear to do. Rodinia 950, I'm just plugging away, get an idea of what it looked like. This is a Mercator projection, so not the globe map. What you see here is, let's see here, what are we looking at? Hudson Bay, Greenland. We are probably located actually here. Actually, we might be right. Oh, this is a very weird orientation. That is definitely Hudson Bay. So we would be here. Yeah, this is this is actually Greenland. This kind of needs to go here, but no big deal. You've got the Antarctic, Australia over here, Siberia, Baltica. These are African plates over here, I believe. And if you want to know what Rodinia looked like in its day, this is probably what the East Coast might have looked like. You had volcanoes, stromatolites, a lot going on, but no plants, no real animals, just basically very simple cell organisms, a lot of degassing. The atmosphere is young, well, it's getting there, but it's starting to look more familiar, but there's definitely, you would not survive there, I don't believe. Not enough oxygen. And I don't even know if there'd be drinkable water, for that matter. Fresh, yeah, I guess it'd be fresh water. I don't know, might taste weird though. All right, so this brings us to beginning of what is going to build New England, and this starts out with the Grenville orogeny, which is right here, And the way this happens is, excuse me one second. That's, okay. Apologies. So in order, I just have an incredibly itchy nose. Oh God. Anyway, um, so what happens here is this is a four-step process, and the first step is the Grenville orogeny, and this is the arrival of Amazonia coming in and slamming into the east coast of the United States. And the reality is that the east coast isn't really here. The shoreline would have been somewhere back here somewhere. And this is from 1250 to 950 million years ago. This is a very old, the Appalachians do not exist. Amazonia is going to come over here, and there's going to be a series of island arcs that slam into this and build a huge mountain range right here. At this point, prior to this, this mountain range, there is just the cratonic area of North America. There is no Appalachians. There is no Rocky Mountains. Maybe Oklahoma was oceanfront at that time. The Lake Erie and Lake Ontario were not even. It might be Huron. Sorry. I sometimes I mix those up. But the Great Lakes would have been close to the east coast where the new ocean would form. So this Amazonia comes in, slams into this, and creates a giant mountain range rivaling the Himalayas. And that stays well for about, well, let's see, I don't know, 1 billion, I don't know, we'll give it 300 million years. And I don't know what's happening with my nose. It is, I don't know. Anyway, so step 2, at about 800 million to 650, Amazonia leaves and snaps off, and the whole east coast of the United States rifts. And that's represented here by these green lines. And you're going to see in the next slide that these really show up tectonically as the mid-ocean ridge. And you'll see it when I go to the next slide, I believe. So 800 million years, Amazonia begins to rift off. It takes chunks of North America with it, most importantly this chunk right here. And you have a series of projections, trajectories, and embayments. And these are important because they define and they make the East Coast look like what it looks like today, although not directly, it's more indirect. So the St. Lawrence promontory is very important because the St. Lawrence River kind of comes out, and it gives the St. Lawrence River, the riverbed is a very solid boundary, so, and a basement, so it's over the years it's managed to flow out and not cut that deep. Yet the whole state of Maine and Nova Scotia were taken away when this rifted. There's basically a large bay in here that filled up when the Iapetus Ocean closed. The New York promontory right here, this is the Adirondack Mountains that still exist today. We still have some of these rocks left over here in very far western Vermont and Connecticut and Mass. And then we have a prominent area right here that basically sticks out and makes a nice basement for Jersey, Long Island, and part of Connecticut. And then you go down, and we have this huge chunk that was taken out, and this is now over on, this is in Argentina. Big chunk of North America ended up going over there. And then you have the area that makes up Alabama, North and South Carolina, and Georgia. But this is where it snapped. This all went away, and basically each one of these was a spreading center. And then about between 480 and 270 million years ago, Africa, well, a series of island arcs, the Taconic, the Acadian, and other pieces of the Iapetus Ocean that got subducted and then uplifted, ended up getting slammed into the east coast of North America. It began around 480, ended at about 270, and built the entire Appalachian mountain range. And I left in here the suture zone, I mean the rift of the Iapetus Ocean here, because when this rifts apart and makes the Atlantic Ocean, it oddly enough it kind of follows the same a similar pattern, which I find very interesting. So Grenville orogeny here, this is what's left of the Grenville. These mountains don't really exist besides the Adirondacks, and that's for an entirely different reason. What the fuck? The Grenville terrain is leveled. It is basically a flat lying area, and I am just got. All right. Hopefully I'm able to edit that. Okay, so Appalachian orogeny, very, very long orogeny. It takes 200 million years for the Iapetus Ocean to close. We build a giant mountain range here again. We fill up the void here in Maine. We also fill up the embayment here that was down near the Ozarks. And then we also build out the Florida Peninsula here because this mountain range sticks well out into the ocean. Because when Africa finally arrives, it also continues over there. And then, between 200 and 170 million years ago, the Atlantic Ocean opens up. And again, when these oceans open, it is not all at once. I mean, it takes, literally millions of years for it to, you can almost hear the cracking when it starts to happen. It takes a long time, and believe me, it's in different pieces. So here is the Atlantic rift right here. And you can see that it's not exact, but it definitely follows a similar pattern from the old suture of the Iapetus Ocean. And so what we have left here is this area gets deformed, this area gets deformed. We have huge mountain range. The whole thing breaks apart, and we're left. The majority of the Appalachians stayed on the North American side, and the England, and Scotland and Ireland. In some of the Atlas Mountains on Africa. Other than that, most of the Appalachians are on the North American side. So that's of interest to know here. So now when this breaks apart, what happens here is interesting. This piece right here actually is not part of North America. In fact, this whole area, I believe right here, is part of Africa. And it ended up sticking behind after Africa broke and left apart. And this is the old Iapetan rift, and it's inactive. Anyway, so that's how it happened. And we can see here, this is what it looks like. This was done back in the late 60s, one of the first globes I ever had. I was just blown away by it. But this is part of the Appalachians here, a little bit of it here. This is more of it up here. And these are the Appalachians here. You would say that this is probably Grenville, what have you, some residuals of Appalachians. But those marks, I'm going to go back. These rift margins are easily seen on this view right here. So you just bring this back and bring this back, and you can see this mark right here is exactly the same thing as what this was and what this was. Over time, it makes a big giant, a whole bunch of marks on both sides. All right. So 1.0 billion years of East Coast North American Laurentian tectonic history. This is something that we're going to come back to. I use it to basically segue to where we are in the time period. And this is an interesting, I mean, this really sums it up. We are going to start here at Rodinia, the Grenville orogeny, in the basically the Neoproterozoic. And then we're going to open up the Iapetus Ocean, and then we're going to bring and close the Iapetus Ocean through a series of Taconic, Silicic, Acadian, and Allegheny orogenies. And they're a little different for the southern Appalachians, but the game's still the same. You're closing an ocean, and there are arcs and what have you coming, and there's a little bit more action going on north until the Allegheny orogeny when that happens. But what's interesting to note here is you have a few things. These are intrusive events. Basically, these are saying that you have plutons being injected into the crust. These Ds right here are what we call delamination events, and they often coincide with volcanic activity and intrusive activity on the crust. So a piece of crust breaks off, goes into the mantle, subducts, melts, and then it releases water, lowers the melting curve, and then we get all sorts of volcanic. So each one of these is really a volcanic or plutonic event. So those are just important to know. And so diverging, so we came together, we split, and then we start to come together, and then we sort of do sort of like a San Andreas fault-ish. As the Iapetus gets closer and closer to close, we shut down the Iapetus Ocean. We have strike slip faults again. One of these big ones is here in Maine, called the Nuremberg Fault. And then this is interesting because right in this area here, a piece of crust breaks off from either North Africa, or we think it's actually the northern tip of Amazonia. A few pieces break off and make their way across the ocean and then end up slamming into North America. One of them is here, one of them is here, and then when Avalonia, which is the microcontinent right here, impacts north. This is basically the mountain building of New England right here, right? The Avalonia, Maine, New Hampshire, Quebec. This is it. This is the main deal. This is actually the Meguma comes right behind it, but right behind Avalonia, when it makes its way over, is the Rheic Ocean. So it's Iapetus, Avalonia, and then the Rheic, and then Africa. So it's a little confusing because I haven't laid it all out, but I'm going to in just a minute. All right, Grenville orogeny. This is the suturing of Amazonia or Western Argentina and colliding with North America. As I stated earlier, this is the mountain, the deformation area. It is huge, bigger than most mountain ranges. That they're bigger than the Himalayan Alpine range, or at least the same size. And this is the entire area that would have been deformed by that. And again, prior to this happening, we're looking at our shorelines being back here somewhere. Shoreline here, shoreline here. None of this even existed. So the Paleoproterozoic. This is 1.65 billion years prior to the Grenville orogeny. The Grenville is the Paleoproterozoic, 1.65 billion years. This is prior to the Grenville orogeny. This is our map right here of North America. Again, no Appalachians, no Grenville orogeny, no mountains yet. Amazonia has not come over, but this is what it would kind of look like. You have the superior craton right here. You've got some of the other cratons sutured, the Wyoming down here. You have the Yavapai, the Mazatala orogeny is right here. Actually, I believe that the Mazatala is right here. It hasn't even happened yet. And you have basically a very small. There's no Rocky Mountains. This is I can't remember what. I forget the Canadian province. Anyways, so to put this in perspective, BC's right here. I believe this is Alberta. So there's no Rocky Mountains, no Alaska, no Northwest Territories. You have an island arc here and an ocean that's starting to close, and this is going to get. You have one island arc that got welded on, and now there's going to be another, and that is in the form of the Mazatala orogeny. This is the Mesoproterozoic, 1.45 billion years ago. The Yavapai has come in. The Mazatala has been right here. And then what we have here is we have an area right in here that is starting to stretch, and it's stretching because of this trench right here. And what it's trying to do is it's stretching this area here. It's causing subduction. The plate's going underneath, and we have a lot of silicic intrusions, granites and rhyolites getting popped into here and suturing this whole area right here. And as that happens, the idea is that this is possibly going to split away. The issue is that it never quite makes it. So as in the initial part of rifting, you get a lot of mafic lava going up into the crust, and then it reacts with the silicic crust, and it melts that because it melts easier, and it just makes a copious amounts of silicic lavas. And then eventually, once the crust thins enough, you'll actually begin to start producing more mafic lavas, and then eventually the crust will separate, and now you're producing only mafic lava. And then once you do that, they'll actually separate, and you'll start producing oceanic crust, and then eventually the water will come in because it will split apart. But that never happened. It basically stopped prior to that. So to give you an idea, we're just looking at this area right here, and this whole area is just loaded with a lot of silicic volcanoes. It's as if the third mountain range was going to start, but it never finished. And then eventually, Amazonia is going to make its way over and close all this. And this mountain range never gets built. It just stops before it even begins. And Amazonia comes in and builds a gigantic mountain range right here, and from all these sediments right here. All right, so Mesoproterozoic period, 1.15 billion years ago. And now we have the Grenville orogeny, and that is represented by this piece of Amazonia here and this piece right here. This may even be a piece of Baltica. I'm not sure. But in any case, they come in, I believe that is Baltica, and they come in and slam and create a huge mountain range right up through here. So you've got trenching right here. You've got stretching right here. You've got, and by the way, these are maps made by Ron Blakey. He is the man for doing ancient geologic maps. And so we're building this piece here and then this piece here, but this piece is much larger than just this. It goes all the way around, and let's just say that this whole area right here becomes a mountain range. So that was represented right here, and that mountain range is our telltale sign that Rodinia has been built and connected. So Rodinia comes together at about 1 billion years, so we're getting there. And so from 12 to 1, you get the building Rodinia comes together, and that's represented right here, the Grenville orogeny. And if you want to get a good look at it in cross section, this is what you would have. This is represented on this little graph right here. You have Amazonia, you have Amazonia, Laurentia slamming into each other, crushing all these sediments, and building a very large mountain range. Some of these are oceanic, some of them are continental. It's basically a melange of just everything. And here's the mountain belt right here. Actually, that's not the mountain belt. This is the juvenile crust. And then we have, this is actually the granite rhyolite province right here. Never quite got built. And then the Grenville orogeny occurs as Amazonia slams in. And then you go to the rifting of it, and part C right here at 9 to 600 million, and you can see that the suture is now gone. So this has now been taken away. But we have a lot of action over here in the U.S. coast where Australia and Antarctica kind of need to bail, and they ripped off of the backside. But that's for a whole other discussion. One thing to note right here is about 1 billion years ago, when after the initial building of Rodinia, we have the mid-continental rift that tries to split the North America basically not quite in half, but it would have done something, but it fails. It lasts about 20 million years, and then it just doesn't do it. It stops. And then this up here, these are dikes right here, big giant mafic dikes and what have you, from an edifice up here, a Pluton called the. Oh, that's not in here yet. This is the Mackenzie. I believe this would be the Mackenzie lip, because the Franklin one does not come in until about 700 million years ago. But this basically shows you got the granite rhyolite. You have Amazonia on its way at 1.3 to 1. Amazonia connects, deforms this whole area, builds this mountain range. This rift develops in here. Probably had something to do with the subduction of crust going under North America from the Grenville event. And then between 9 and 600 million years ago, Amazonia is separates. So we go from here to here, and then at 600 million, we get a passive margin that would be, basically somewhere between here and here. The arc is not formed yet, but that's going to come up very soon. So the Grenville orogeny representation on the Wilson cycle is here. We went through all the phases, and then boom, that's the Grenville continent collision, giant mountain range. Grenville orogeny affected terrain. So this was a huge orogeny, as stated earlier. You've got area of deformation all along the East Coast, all the way down into Mexico. You have a whole bunch of things going on this map right here. You're showing the Trans-Hudson orogeny, basically mountain building episodes between 2.0 and 1.7 billion years. Then you have the baby of the group, which is the Grenville, which is between 1.2 to 1.0 or 900 million. You have the Mazatol and the Yavapai down here. You've got the mid-continental rift. These are what we call proximal deposits. They're deposits from these mountain ranges, and they're kind of going into basins. And this is one of the ways we know that there was a mountain range there. This is sort of the cross-section of it. 1,200 million years ago, Amazonia is here. It's subducting. The ocean is subducting under Laurentia. We've got slab drawback here, or not slab, but we have thinning of the crust here. We have the continent here. We have the subducting oceanic crust, and this is eventually going to slam into this. And here we are. It does slam in, and now we've got all sorts of deposits coming from this mountain range that's building. This is the suturing of Amazonia and Laurentia making Rodinia, and then eventually it splits. And again, each one of these produces sedimentation because you have either things being pushed up or things being pulled apart and going down. And either way, whatever void is made, these basins get filled with sediment from these mountains. So obviously when this splits apart, you get a little piece sort of here. You got the mid-ocean ridge here. You have another subduction zone over here. But anywhere in between these things, you're getting sediments derived from these mountains that are being built. Another Grenville deformation map. Fact that these cross sections are going to come in handy in a few minutes here, but this is just showing you the areas that were deformed. This is the Appalachian front. So in other words, when the Appalachian Mountains come, this is what we call I believe this is the Cameron line, and then everything back here was deformed from the Grenville. This is the Grenville mountain range. This is the area where it basically bent it all up when it intruded. We have some residual pieces from the Proterozoic down here. You got some slivers. I think I'm not sure what that is. But these are, oh, okay. These are just residuals of the Laurentian continental, I want to say the shelf, but the edge. And these are pieces that were um, basically pushed up through when this occurred. I would think that these are actually pushed up when the Appalachians came and these punched through or deformed or slid up over younger rocks. Because that's 1.5, 1.6 billion. Yeah, these are basically when the Appalachians came, these pieces got punched up through. But anyways, force was this way: Grenville, Grenville Orogeny, Grenville Front, and then you have the Appalachians, which have not been built yet, but they're going to be built. Yeah, Cameron's line runs right through here. This is what we refer to as the suturing of the Iapetus Ocean. Or basically this is the extent of the North American side of the Grenville orogeny. Anything after this was accreted in the Paleozoic, and it is beyond everything over here this is North America, Craton. This is what we refer to as juvenile terrains, i.e. the Appalachian Mountains that have not been built yet. And we use this as this line as basically say anything west of this is North America proper. Anything to the right is an exotic terrain. And that's true. All right, this is a very complicated map, but the gist of it is it's showing you have the mantle here, you got the moho. These are different densities. One floats above over the other. This is North America. I'm sorry, this is the Appalachians and the Gondwana basement, so probably pieces of Africa here. And you basically have these pushing this way, which is forcing this to slide over this, which probably, yeah, this is going to slide over and this is going to thicken here. And then you have exotic terrains here, a few, and then you have the Grenville right here. And this is a giant thrust fault that's under me. Basically, this is going up and this way, and this is going this way. And then you have a giant thrust fault here. So, continent. This is a continent arc collision. This is more towards. Let's just say that this is more north, maybe Canadian, maybe even mid-Atlantic. Well, I don't know. Let's see. You got continent arc collision. Okay, I see how this is. This is almost done in time. So you have the Grenville orogeny here. You have Gander. This is a piece of North Africa. This is an island arc right here. Actually, I'm sorry. Gander is a piece of how does that go? Oh God. Gander is a piece of the Iapetus Ocean mixed with island arcs and probably pieces of Amazonia, or at least close to it. So what I think is I need to go back here. All right, so we got B, C, A, B, C, D. Okay, so D is there. All right. So these are just matching up at different areas of the North America cross-cutting the Appalachians. And the gist of it is I would say that, so this is a continental arc collision. And what's happening here is forces coming from this way. It is pushing Gander, overriding the upper mantle, which is now overriding the Grenville thrust belt. Here you have Avalonia pushing Gander, which is crunching more the tectonic belt. And over here you have the final stages where you've got Gondwana, you've got Avalonia here, you've got Gander, you've got them all right here, and then this is just forcing this whole thing up over the craton in North America. So, in a sense, it's kind of like this is the beginning, this is the middle, and then this is sort of the end. But um, it's more like, how to explain this? I gotta look at that slide again. So E is there. All right. So if E's there, yeah, yeah. E is pretty much in Maine. This is in Canada, and then this is the U.S. Grenville province down in the Southern Appalachians. So Southern Appalachians, Canadian Appalachians, and then you have the New England area. So this is New England, Canada, Southern Appalachians, and that's just showing us the way that this affected. And this is right under Maine. This is a perfect example of Maine. You got forest from this way. Gander is a big chunk of Maine, and it drives into the Taconic Belt, which was the original belt that came through, and it's forcing everything up over the Grenville province. So that makes sense. And if you go a little further north, you've got Avalonia, Gander, and then you have the Taconic. And when you go down further south, there's not much Taconic because there's more continental crust down there, and the Grenville Orogeny is riding up over North America because Amazonia pushed it further in that area. Apologies if I did not explain that well, but that's what's going on. We're not even going to look at that. That is just way too complex. So Rodinia breakup. Around 750 to 850 million years ago, Rodinia has run out of gas, or the driving mechanisms that have forced it together have run out of gas. And we are now starting to see the mountains flatten. And as they flatten, the crust thins, and then you have decompressional melting. And we have rifting starting right in here. This is the Rentia. We would be right here. Amazonia is right offshore, and it is now starting to move away. It is starting to go south, I'm sorry, southeast. And it's also separating from Baltica and West Africa. And everything is sort of rotating in this direction right now. So everything up here is going this way, everything down here is going this way, and the whole thing is, as a rule, is kind of separating. And then over here we have Australia, India, and Antarctica. They are now leaving North America right here. There's a huge rift that opens up right here. And this is, you can think of this as from like Colorado, Utah, Montana. This separates. As I said before, you usually get a 120-degree 3-rift break. You got one here, you got one here. Looks like you may have had one here. You had one here. And eventually 2 of them will work, or maybe it doesn't really matter. But anyways, these are going to separate, and they're all going to go their separate ways. And this is the beginning of the breakup of Rodinia. And these are arcs in the Neoproterozoic, and these are signs of a whole new issue of subduction happening. And these are going to start changing the direction that the southern continents go, as well as India. So now we've gone from here, progression stages from the Grenville orogeny to the Iapetus opening. We go from here, thickening, the orogeny. The orogeny runs out of gas, it begins to thin. Decompressional melting comes up, you start to get plutons and stuff, the continent begins to flatten out, and then eventually, when this gets thin enough, it really starts to be pulled apart, and we get rifting, and this is the opening of the Iapetus ocean, and eventually it's going to open, and then it's going to shut, and then we're going to build Pangea. So Grenville rifting event, opening of the Iapetus ocean, is represented by this period here, and we are now going to move over to here. And we're going to get an island arc offshore, and we're going to start to close this is the Iapetus Ocean. And what's interesting about this is that it is this long, broad area of calm water and a passive margin that really life begins to, it appears that this is the one thing that really gives life its kick, because for the last billion years, it has not done much. It's been single cells, and it went to double, to single cell organisms to, they went from single cells, they're prokaryotes, to eukaryotes, which are multi-cells, to multi-cells that stack. And when there's volcanics and catastrophe, life has a tendency to get set back quite a bit. You know, if you're a newly evolved organism, you know, the stromatolites have figured it out. The cyanobacteria have figured it out. But new cells and new ways of life have yet to figure it out. And so, but it's this passive margin off the east coast in the late Proterozoic and the Cambrian period that really give us the kick of life. And if you want to have an idea of what this looked like, we have from all the way from New York City up to up past Vermont, right along the Connecticut or the Vermont, Mass, Western Mass, and Western, all Western Vermont borders. There's a huge area of marble, you know, hundreds and hundreds of miles long, and 100 miles wide, and that was a gigantic reef area, kind of like what you see down in the Bahamas in Florida right now, in Fiji, and it got compressed and metamorphosed from limestone to marble. But it was the water quality there had to have been just spectacular. Beautiful blue water, lots of sunshine, lots of warm stuff. Critters love it, or things that are going to become critters love it, and it gives life a chance to get a kick. And this is kind of an idea of what Laurentia might have looked like 700 million years ago. You know, again, it's still pretty foreign, getting there, but life is still pretty much single cells, a couple eukaryotes and stromatolites, and lots of volcanoes. So the Iapetus Ocean rifting event. The Iapetus Ocean, as I said earlier, opens up along a rift right here after the Grenville orogeny from about 800 to 650 million years ago. And in the process leaves promontories and it leaves embayments. And this is just a picture of the rift event. And again, this did not happen. Like I have another chart that has all the different isotope readings, basically giving the dates of the lavas that are associated with this, and they're over a 200 million year period. So when you look at this, you can almost hear this cracking as it opens, but it like one open here, and then one open here, and one open here, and one open here, and it's all over the place, and eventually they kind of team up and then they split. I mean, you can see intrusions here, right here, right here. You have a big rift right here. You got another one over here. These are ones that tried to go, but they didn't quite make it. So this is the Iapetus rifting event, very similar to the Atlantic rifting event. That's going to come about 600 million years later. And that's represented by this this little bullet here, or whatever you want to call it, X circle thing. And the Iapetus right here, this is the opening event. You have the marker where we are in time, and of course lots of intrusions are associated with that. And of course, boom, there they are. Intrusions here, intrusions here, intrusions here. This is all associated with the rifting of the Iapetus Ocean, and actually, the entire area of north and south of the East Coast had Amazonia ripped away. And now we're going to work our way up and start to close the Iapetus Ocean. All right, so this is the late Precambrian, 550 million years ago. Again, this is the equator. We are way below the equator. We're the South Pole's over here somewhere. This is Amazonia, South America, and it is now beginning to rift. It is separating. It took pieces of it with it. We got a chunk right here missing. Florida's not there. We got you got the Alabama embayment here, and here's South America. Here's Baltica, and it's like I said, three-way split. Boom, boom, boom. And all three of these are going away, and we're going to start. This is the Iapetus Ocean right here. All right, Neoproterozoic period. This is the global view. 560 million years ago. Now you have the Iapetus Ocean. You are right here. You've got Baltica, you've got Siberia, and this ocean is going to open. And again, now Amazonia is actually on the South Pole, and we know this because there's a lot of we find glacial tillites on these continents from around this period. So there's also some very large ice ages that were associated um, in the late Neoproterozoic. I mean, there's one. There's a Saturnian, the Hunterian. These ice ages lasted like millions of years, and we think a lot of that had to do with um, when Rodinia came together. It literally had a lot of land that was on the South Pole, and so it probably contributed to a glaciation, a worldwide glaciation at that. So now here we are. We're at the passive margin at 550. You've got the Paleozoic, the Proterozoic passive margin. However, what we don't see is way off in the distance, somewhere a couple thousand miles away off of what is now Amazonia and Africa, and they're kind of connected together now at this point. Oceanic crust is beginning to subduct off the coast of that, and it's going to start to create an island arc, and it's going to start to pull it across the Iapetus Ocean and slam into us, which is going to make this. This right here, the force looks like it's coming this way, but what will happen sometimes, you have what we call slab rollback, and as this drops down, this thing just has no choice, but it starts moving this way to fill the gap. And so it separates from here, it drives itself over here, and then it slams into here. This would be, North America, Laurentia rather, and you have this first mountain building event. Here's the sediments, they've been crunched, the oceanic crust has been crunched, and the island arc has been crunched. And this is called the tectonic orogeny. And this is the mountains of the Green Mountains of Vermont. I mean, that's just the best way to think of them. The Green Mountains of Vermont are the tectonic orogeny. It goes up into western, very, very tip of western Maine, but more so in Quebec, and a little bit into Mass and Connecticut. But for the most part, the majority you see it is the Green Mountains of Vermont. And the North American East Coast at 550 million years ago is a nice wide spreading center. And this is what probably much like what we see today. Big old giant wide spreading center. But what we don't see is that way over on the other side of the ocean, this is beginning to occur. So we're going from here to here. And if you were to get a cross-section of what North America East Coast looked like, or the depositional environment, this is what the Grenville Mountains were. They've been eroding for a very long time. They probably were worn quite low by this point. It doesn't take that long to wear down a mountain range. You've got a huge amount of carbonate coming off of this. And the carbonate is going into the warm shallow sea with a nice warm temperature, and it is allowing the excretion of carbonate organisms. And you're starting to see the first signs of carbonate organisms form in the warm, shallow seas off the East Coast in around 550 million years ago. So this is the Earth around 600 million years ago. You're starting to get a nice warm blue sea. You've got a volcanics out here. This is what it would look like. The world is starting to look a little bit more. If you have a blue sea, you still got your stromatolites. There's nothing on land. There's no plants. And life is still very simple and only in the oceans. But that is about to change. This would be the North American East Coast 560 million years ago. Passive, calm, warm, very clear tropical waters that produce massive carbonate reefs that are later metamorphosed into marbles. Found in eastern New York, Vermont, MA, and Connecticut. Yep, that's true. All of it. And we are now going to give rise to the Ediacarian biota. And I am going to end this lecture here because I have gone on for quite a while, and this is an awesome subject. So we're going to stop that right there. And we're going to come back to the Ediacarian life. This is the Ediacarian right here, and just a quick synopsis of this. We really consider that true explosion of life took place about 540 million years ago. However, in about 580, we have the precursors of what we see today. However, they're different, and they're not 100% relatable to the things we have today, although we're starting to find more evidence that they are. But this is a group of animal and plants, we think animal, but they do have animalistic qualities to them, some of them, um, that occurred prior to the explosion of life in around 541. Around 541 million years ago, we have almost all animal families represented, although they're very primitive. Um, but there's almost a a 20 million year gap where you go from these. They look like it's not even really a sponge, but they're just very primitive things that have a tendency to either float or they're anchored or they're just sit on the bottom of the ocean. And they're very, I don't want to say they're simple celled organisms, but what they are is they tend to have a tendency to have all the same cells, but they're stacked. They went from single cell to multi-cell to stacked. And this is the period where life was trying to figure this out. And it figured that if it could use more cells of the same thing and make a bigger organism, if you want to call it that, maybe it stood a better chance for survival. Um, and that is the Ediacarian Biotas. We have things that stick up out of the sand or the mud. We have things that lay down on the mud. We have things that kind of float around. But there's really no head. There's really no mouth. There's really no digestive. And there's really no anus. They're just very simple. They're not quite what we see today. But this phyla and this group of life forms is absolutely fascinating to scientists because it's as if life tried to get it going only to have it stopped and taken away because these do not make it. These actually go extinct prior to the explosion of life. And that's what we're going to talk about next.